So hello everyone and welcome to the HamSCI Zoom Telecon. I'm glad to see everyone here. Welcome once again. So we have two people on our agenda today, and the first is going to be Ward Silver and 0AX giving us an update on the YASME funded new RBN nodes. And second will be Zach Leffke from Virginia Tech talking about antennas that he's designing. So why don't we start with Ward? Go ahead and take it away. And I have to unmute you. So I've taken the liberty of muting everyone. So if you want to speak, you have to unmute yourself.
There you go. You have control of the vertical and the horizontal. Okay, super. Basically, little background. I'm the president of the YASME Foundation. It's a U.S. nonprofit 501c3 that is dedicated to helping groups and individuals and whatever with small to medium-sized projects that advance amateur radio in some way. Our goal is not to go after the big splashy projects which get a lot of publicity. We're more interested in small things that have a high multiplier, so to speak, and further the interests of amateur radio at large. We are at yasme.org. The name is from the sailboat of Danny Weil, VP2VB, who was the first of the major expeditioners, serial expeditioners, I guess, after John Dennison, W0DX, and Bob Leo, W7LR. Anyway, back in the mid-50s, Danny sailed his boat around the Caribbean and the Pacific and other places and put them on the air, which was quite a feat back in those days. The foundation was formed to support his efforts and then gradually morphed into what it is today, which is a mechanism for funding various interesting projects. One of the things that we supported a few years ago was the rebuilding of the Northern California DX Foundation's beacon system, which operates on the HF bands at 20 meters and up around the world. If you go to their website, ncdxf.org, you can find it. And in between that and now, this thing called the reverse beacon network came along. People started putting these automated CW skimmer receiving nodes around the world, and then that was collected into a network and the measurements placed online as database. And Nathaniel got a hold of that a few years ago and started writing some papers about it and found that there was real value in this data set. At the time, how many nodes were there at the time, Nathaniel? Maybe 50?
Oh, maybe about 50. I think about 100 or so.
Yeah, 50 to 100. So you could clearly see the effects of solar flares and other space weather phenomena on the changes in signal strength reporting by these individual nodes. They record signal to noise ratio, not an absolute signal strength. And the receiving equipment is basically all over the map. There's everything from SDR dongles, RTL SDRs, all the way up to fairly sophisticated SDR equipment. And the antennas are anything from little whips to rather large arrays. So what's important is the delta between the readings. Anyway, this has become very useful. It was put to work during the Solar Eclipse QSO party in 2017 and really got the attention of the research community along with the help of Nathaniel. So this has become a thing larger than its original scope by a factor of a lot. And people are starting to pay attention to these things, not only to put out who can I hear spots right now, but also how well can I hear them? How do they change over time? How do they compare to other transmitters? And how do the readings at different node locations compare? So if you look at the map of the reverse beacon network nodes, you can see most of them are in Europe and North America. It's a volunteer thing. It's mostly been to the interest of DXers and contesters, not so much the scientific community. And so it's been the HFDX and contest community that's put these things up over time. They're starting to spread. There's some in Japan. There's some along the Pacific Rim. There's a couple in the north part of South America, various places. I see V51YJ on our list today. Andrew has one up. We had one in Liberia, EL2BG, that's currently off the air. I don't know if a receiver can be said to be off the air. It doesn't actually transmit. It's sort of not listening to the air, I guess, at the moment, maybe moving to a new spot. But if you look at the map, you go, man, there's a lot of places where there aren't any nodes. There's no receiver there. I wonder what we could do about that. So what I suggested to YASME, we funded a few nodes. We just sent a package of 3 to ASH, 3 Victor portable KF5 EYY in Tunisia. And ASH is coordinating a group of students in Algeria, Tunisia, and Libya to put up one of these packages. They're very small. They're just a whip antenna, a red pitaya, SDR, which is a general purpose signal processing platform, and a PC that runs the CW skimmer software or the RTTY skimmer, and an aggregator package, which is the software that takes the output of the decoder software and sends it to the reverse beacon network server. And that's run by a team that includes KM3T, PY1, I can't remember what Felipe's call is at the moment, Pete N4ZR, and some other folks that run the server. And then that database is available either to the international spotting networks or to individuals. So you can download the data set you want. So we looked at this and said, a lot of empty spots. I wonder if there are spots that would have high scientific value as well as filling in a hole in the ham radio who can hear who network. So I talked to some of the folks here in the HamSCI leadership, Phil Erickson, Bill Lyles. I don't think Phil's here today, but Bill is. And we had a little discussion, and basically there was a lot of interest in the nodes that were proposed in Russia along basically along the old Siberian railway, Trans-Siberian Railway line that goes just north of Kazakhstan and then out by Lake Baikal and all the way out to Khabarovsk. So several individuals expressed an interest in putting up a node, and some of the other board members of YASME were out prospecting as well. And we have active interest from 11 of the Russians, including RW9AV, who's on the Yamal Peninsula, which is northeast of Murmansk. It's hard to conceive of something be north of Murmansk, but it is. And so that would be an Arctic point. And we have a fellow in Mongolia who's interested. We have Angel, WP3R, who's down in Puerto Rico. Fred, K9VV, also known as NP2X on St. Croix, and a couple out in the South Pacific, 5W1SA and 3D2AG are both interested. And we also have interest around South and Central America, and our board member, Hans Zimmerman, PB2T, is working with several people in different countries to find locations for them. We have a couple more in Asia, Nodir EY8MM in Uzbekistan, I think, or maybe it's Turkmenistan. Anyway, it's just north of Afghanistan. He is very active and wants to put one up. A4 in Oman, Oceania, a group in Oceania is putting some nodes on the air, including one possibly in Darwin, which is all the way at the north part of the country and very close to the geographic equator, and that might be particularly of scientific value. And then Africa, we're trying to get the EL2BG node moved to a new site, and we have a potential host in Zulu 8. So progress, there's a lot of interest. These nodes cost about $1,500 a piece, depending on whether you need a PC or not. You need some internet, but really the volume of internet traffic is rather low. The spots consist basically, each data point consists basically of a text string that's about 80 characters long. So the decoders just pile all this into a file, and the aggregator software stuffs it into the server. The PC has to have 100 megabit per second Ethernet connection to communicate with the SDR, which is in our package a red pitaya, and then the antenna at this point is an active whip vertical manufactured by DX Engineering. It's a standard 108-inch stainless steel CB whip and an impedance converter amplifier that takes the very high capacitive reactance of the whip and converts it to 75 ohms to drive low loss cable TV coax back to the red pitaya. So we have 15 in this latest package. The board approved putting 15 nodes out there. We have, I think, 12 of the candidates have signed up. We require that they acknowledge they're receiving the equipment, that they're going to put it on the air, that they're going to maintain it to the best of their ability, and try to do this for a fixed period of time. That's required of us as a foundation, since we are making a contribution to an individual and not another nonprofit. We're on the hook to make sure that the money is spent in accordance with our charter. So you have to be careful about that kind of thing when you're in the money giving away process. So we have, I think, 12 of the 15 nodes all signed up for that. We have some backups, and I expect additional nodes to be funded next year. We may start something like a GoFundMe page where people can contribute to the effort to put more nodes on the air. So hopefully this will become very popular and get completely out of hand, and we'll have lots and lots of data, and we'll have a big data set for the total eclipse in 2024 and other interesting events as the new cycle comes online. So I think I've talked for about 10 minutes straight here and pretty much dominated things. So I'd like to open the floor and answer questions and see if you've got some suggestions. Not all at once.
Thank you very much, Ward. People, please feel free to unmute yourself as you have questions.
What was the name of the website again, or the address?
YASME, Yankee Alpha Sierra Mexico Echo.org. YASME.org is the website.
I'm bringing that up now.
There it is. And that's, I think her name is Yasmin. She's at the Ethiopia Club, ET3 Alpha Alpha.
Cool.
Yep,
Thank you.
that's a picture of Danny's boat there, the first one. He sank 2.5 of them, and the third one finally survived. Other questions or comments? If you have suggestions for node locations and hosts, let me know.
So, question about RBN things. It used to be that you could go to the RBN website. Thank you, Nathaniel, for pulling that up. You used to be able to go to the RBN, bookmarked, perfect. The RBN website, and yeah, there it is. What happened to the map? Well, what happened to the map was that Google Maps used to offer support for having Google Maps for free, and I have a nice screenshot here that shows how this used to look and is really a wonderful example. I'll just drop that into the chat. Yeah, if you look at the link that I just dropped in the chat there, it shows a test that we did a few years ago that is, I think, a good example of this, where you can see all of the 20 meter going to one side of the terminator and all of the 40 meter going to the other side. And I've been thinking that it might be fun to see as a concept for a short paper if usage of the RBN dropped the day that Google Maps stopped supporting that map. But more to the point, is anybody currently working on an open source replacement for this using Leaflet and OpenStreetMaps? Because that seems like something there really ought to be. And I'd be willing to put in some time working on that if somebody else would be interested. Certainly, if it's not a project that's in progress, I think it ought to be, because having that ability to look at the map in real time was always so useful. I would go and I would hit the RBN button, and then I would see the map very clearly of where the signals were going.
There is some work going on. You should talk to Pete, November 4 Zulu Radio. He is the contact, and he will put you in touch with whoever's working on it and whether they could use some help or not. In addition to just the map of the nodes and that kind of thing, all sorts of visualization tools would really bring this to life. Another package that I'm aware of that does great visualization in real time is ViewProp, VIEWPROP. It was written by Rick ZL2Ham. And yeah, there you go. And Rick does some really good stuff. It's a free software. YASME bought him some software tools a while back. I don't think it's in active development right now, but it seems to have a user base and seems to work pretty well. So those are the two packages I'm aware of, along with dxmaps.com.
Do they have that set to, why not put this on the website directly? Does this run offline, or is it pulling from old databases, ViewProp?
ViewProp will either, let's see, as I recall, you can give it a file. It'll play back a file like a log. It can watch a certain telnet node to grab spots off of that. And it can also, in real time, look at your contacts and use a QRZ.com subscription to come up with the locations. And I think the whole package is based on EI8IC's mapability software.
All right, thanks very much.
You bet. Cool stuff. I like looking at stuff. By the way, if anybody puts together a public demonstration package, like at a museum or some kind of site where the display is occasionally staffed, but if you could put that kind of a display that runs all the time on a big monitor or something and let that run behind glass or something like that, people really get that. They understand the idea that the different colors mean different frequencies, and the different points are a contact, and they like watching it. It's a pretty cool thing. So that would be a neat feature for a display or a demo of amateur radio.
So following on to that, this is a figure that I just put together about a week or so ago. It is, still very much unedited and raw, and we don't, fully know how to interpret it, and it still has, missing stuff. But what it does show is this is a whole solar cycle's worth of both RBN and WhisperNet data. So observations. So we are looking at from 2009 up through 2020 here, and it's split up by ham radio band from 1.8 to 28 megahertz. And along each y-axis is the transmitter to receiver distance, so the communication distance from 0 to 10,000 kilometers, and 11 years of observations this way. And then you can see over here in the map, this is a heat map of all 11 years of data for each band. So if you wondered what everything looked like for the past solar cycle using these data sources, this is it.
This is really cool.
That's excellent, Nathaniel.
Yeah. So
Anything
I think
people can think of with to visualize stuff We need to be constantly making sure there's a public data port of some sort. Either the data can be downloaded as a file or accessed in real time, and let people's creativity really bloom on this. What were you going to say, Daniel? Go ahead.
So I think a couple things that we were just speculating. Ethan Miller was speculating that these little spots down here are probably sporadic E on 28 megahertz and maybe even on 15. And I think it was Phil Erickson that suggested that you see this sudden drop off where all of a sudden, you know, right before 2016, there's a cutoff in 21 and 28 megahertz spots. And he was saying that's likely because the solar cycle daily MUF just basically dropped below these two bands all of a sudden. And so you can see a really dramatic drop off in the amount of activity there right after 2015.
Interesting. What does this mean? Yes.
Yeah. And the other thing that's interesting from the point of view of where do you put RBN nodes and where do you put operators and whisper, yeah, basically operators and receivers. If you look at this map, these heat spots, they represent the midpoints between transmitters and receivers. So wherever you see a hot spot, that's where you have the most midpoints between a transmitter and receiver. So it's very heavily weighted over the United States, over the Europe, and people talking between the two. So, and very much weighted toward the Northern Hemisphere. So, you know, we really need to try to do things to encourage both operation and receivers in the Southern Hemisphere. And you can see that is a part that's very much missing from these maps. And if we had that information, there's a lot of interesting studies that can be done. You know, there are certain both symmetries and asymmetries between what we expect to see in the Northern Hemisphere and what we expect to see in the Southern Hemisphere. And if we had better coverage between the two, we could do some of those comparisons much better than we can now.
Phil Karn, KA9Q, who's also the president of the Amateur Radio Data Corporation, ARDC, that's been making some grants. Phil spearheaded a little project to put a floating receiver into the Pacific Ocean off of California, and they're tracking it. It phones home every so often and gives its coordinations, but it's got a satellite phone on it, and it could be an oceanic receiver. These things would drift around, but you'd have some data from them, so that might be fun.
That'd be really cool.
It's the kind of thing that really gets the attention of students and technical people who are wondering what there is to do in amateur radio and if there's anything really of value out here. We, you know, we have our traditional means, but there's a lot of new technology out there now that's starting to make things really interesting. So let 1,000 flowers bloom. Back to you, Nathaniel.
Thank you very much, Ward. That was an excellent talk. I think, so it's now about 3:30, and we do have one other talk. So if there's any last questions for Ward before we go on to our next speaker? Well, if you do have any questions for him or you have input on where to put new RBN nodes, you know where to find Ward through email and also available on the HamSCI list. So next we have Zach Leffke, I think Kilo Juliet 4, Quebec Lima Papa. Is that right, Zach?
Yep, yeah, that's me. I'll go ahead and grab the screen here.
Great. So Zach is a you're currently a research engineer at Virginia Tech, but you're going to be pursuing your PhD soon. Is that right?
Yep. Yeah. So actually, let me first of all, can everybody see the screen?
Yes.
Hopefully, you can now see a kind of full screen here. Yeah, so the quick introduction for myself, as Nathaniel said, I'm research faculty. I actually work for the Hume Center for National Security and Technology, but we overlap a lot with Space at VT. Nathaniel and I used to run around doing club stuff together when he was at Virginia Tech. So all great stuff. Yes, recently I did decide to pursue a PhD, but I'll be staying full-time as faculty. And I guess my formal title is research associate. Yeah, so I'll be going after a PhD, but that'll be a very long process because that'll be, I won't be a full-time student. I'll be full-time researcher, part-time student. And with that, I'll go ahead and dive into the presentation here. I do have something like 40-ish slides, but I'm going to try to keep the talk to about 10 minutes. So I'm going to be burning through a lot of slides. I'm hoping that I can send these out to Nathaniel afterwards, and then people can read through some of the stuff at their leisure.
Yeah, I'll be happy to post this to the HamSCI site.
Perfect, excellent. Okay, and yeah, a lot of the reason there's so many slides is there's a lot of pictures, which I'll show kind of towards the end. So with that, here's the agenda for the presentation. I'll do an introduction and overview of what I've been up to over the last few weeks, or maybe month or two, and give the kind of a quick description of the schematic and the PCB. I took an entire week of leave just to do extensive benchtop measurements of 3 of these boards, and just to make sure that everything's behaving the way that I expected. And then kind of towards the end of that leave period, I was able to do some on-air tests with the antenna that you guys can see in the kind of bottom right of the screen. So that's where a lot of the pictures are of comparisons against, I believe, I forget the exact model number now. It's a commercially available ICOM tilted terminated folded dipole. You can kind of see it in the background there on the, just above the little pyramid. And then also the active magnetic loop from DX Engineering. So kind of real quick spot checks of just quick anecdotal, what's the difference between my antenna and their antenna. So for the introduction and overview part, I crammed a lot of information onto one slide. Basically, everything I've been up to is heavily influenced and inspired by the long wavelength array. They have a really good memo series. It's hosted by Dr. Steve Ellingson from Virginia Tech. He was a big part of the LWA design. He's already, I gave him a heads up that I was giving this talk and some of the details, and he already gave me some ideas for improvements. So that's kind of future work. So there are the links for where you can find the memo series, specifically the one that's LWA 0190. There are about 200 documents on that page. The 0190 is a collection specifically about the active Balun design, which mine is a kind of variant of it. The bottom right table shows the sort of design deviations that I went ahead and took. The LWA front end actually goes up to something like well over 100 megahertz. They say on their kind of the actual long wavelength array that they're targeting the 10 to 88 megahertz spectrum, but we obviously want to go a little bit lower, and we don't need to go quite so high, particularly, and I'll get into this when I talk about the filtering, with AM and FM rejection. They also use a fairly expensive 180-degree hybrid device. I opted to go, I want this design to be very cheap, very easy to reproduce, that kind of thing. And the current design, you can see on my GitHub link there, is where the KiCad for everything is posted. I might have a, and I think I even got the address wrong there. I might have a WordPress site soon, coming soon as TBD. I'm doing all this on top of all the full-time work, so we'll see when I get it up. I might kind of move the documentation over to there eventually. And then the left is kind of the cost breakdown. So for those that use OshPark, you know they have this ×3 rule where you order boards in batches of 3. So that's kind of like the minimum cost. So 3 PCBs, the minimum cost would be about $37. If you did like a group buy with somebody, that would be about 12 bucks and change for a single active Balun. If you want to do each polarization, each linear polarization requires 1 Balun. So you need a minimum of 2 boards to do like a dual polarization setup. And then I give the Mauser DigiKey kind of parts list breakdown, which the detailed list is actually on the GitHub page with the bill of materials there. I might even, once I'm satisfied with my revisions, I might even make the OshPark PCB project public, and then that way you don't even have to worry about downloading KiCad and then uploading Gerbers or anything like that. You can just click order on the OshPark page and get a board sent to you, or get 3 boards sent to you. So overall cost, I'm estimating right now about 150 to 200 bucks. That's for everything. So if you ordered 3 PCBs, or say you did a group buy and you have 2 PCBs and you ordered all the parts for 2 boards, that's about 100 bucks-ish. That's the 12 bucks plus the 71 bucks. But then there's the extras for the PVC enclosures and all that kind of stuff to actually get the thing up and on the air. I'm not counting coax in that cost. So that's basically what you see in that picture that's made out of PVC, roughly 150 bucks. I went ahead and I had this at the end of the deck, but I figured I might run out of time, so I went ahead and moved this slide to the front of the deck. This is the overall sort of very high level 1-page shot at the summary of the overall features of the active antenna. So I was designing for about 1.5 to 50 megahertz. The filters actually came out around 4 to 47.5 for the 3 dB bandwidth. About 36.1 dB gain, which is right in line with the LWA stuff. Noise figure is about 3.87. Yada, yada, yada. You guys can read all these details. The main way that you supply power to it is via the coax, so you reduce costs and having to run extra cable. You also get some shielding out of that by running the DC power through the shielded coax on the center conductor. Kind of standard stuff. But all these numbers kind of came out roughly as expected. Again, this isn't really my design. It's just a tweak on other people's design that's also really well documented. And so the good news is what I did, I didn't screw up when I made my own schematic and layout and populate. Actually, I did screw up, and I'll show you that here in a minute. But overall, things worked out as expected. Here's the kind of high-level concept of how it works. So you have 2 active devices. This is all for a single polarization, so a single Balun board. It took me a while to figure that out and make sure I was understanding everything properly. So there is no active element and radial. It's 2 active elements per single linear polarization or single dipole. Each gets its own Galley 74. There's also a line driver with the Galley 6 amplifier, and then I have my bandpass filter after the combiner. And then there's a kind of integrated bias T for doing that DC over the coax. So that's a really high level sort of basic idea behind how it works. This is where I get into the design deviations for from the LWA low pass filter that's part of their design, which is kind of represented on the left. And then the bandpass filter design that I use for my design on the right. This is I use Quux, which is a quiet universal circuit simulator, and they have a really nifty kind of quick and easy filter design tools and simulation stuff. That's the other thing. All of the tools I'm using, this is the first time I've done a presentation with LibreOffice. So if it screws up, I apologize. But I'm trying to make everything open source. None of this, other than where noted in the deck, I'm staying away from using things provided by the university and trying to make it all open source, open hardware, all that kind of stuff. So Quux is the simulation tool I use, not some super expensive thing that I happen to have access to because I worked at Virginia Tech. So the Quux simulations themselves are also posted on the GitHub page, so you can pull those and tweak the design, run your own simulations. The bandpass filter did not work out the way they rarely work out the way they look like they're going to work out when you simulate them. So I'll get into that a little bit more in kind of the results section. But basically, the basic goal of the bandpass filter is doing what it's supposed to, which is rejecting the FM band and rejecting the AM band, which the low-pass filter and the LWA design does not do. And this is for the actual, and I'll get into this more ahead here, you can actually select a low-pass filter or a bandpass filter with the current version of the design. So both of these are on the board, and these are the simulations of them. Both offer about 30 dB of rejection at the FM, broadcast FM band, right around 100 megahertz. But if you don't want to notch out AM, or if you know you're in a really quiet area and you're not concerned about AM, you don't have to use the bandpass filter. You can switch over to the low-pass filter, and that's all accomplished via solder jumpers, which I'll show more of here in a minute. I won't linger on this slide too long. This is the overall schematic. This entire thing was in the LWA memo series. I literally just copied it and then tweaked things for my design. The biggest tweak being kind of down in the bottom left, where the options for the solder jumpers for the filtering is included, but everything else is nearly identical to their design. One deviation I did play with, and I mentioned higher up, is I used an 8-volt regulator instead of a 12-volt regulator. And the reason I did that is I could foresee a scenario where you're doing like portable operations of this possibly. And if you're running off of batteries and they drop below the dropout voltage for a 12-volt regulator, but you still want to keep going, you might not want that kind of 12-volt cutoff. LWA, right, they have a very solid infrastructure for everything. So they have a 15-volt power supply with a 12-volt regulator on the board. I went with an 8-volt regulator, which meant I had to adjust the bias voltages for all the amps. I also messed around in the schematic. I was trying to basically make things run a little hotter because that should have improved the linearity a little bit. There was no real major effect there, so I kind of went back to the recommended datasheet values. So there's a deviation that'll show up in future revisions where the 3 bias resistors for the galley devices are actually 39 ohms in the results I'm going to present, not 30, 30, and 33 ohms. So that's the overall schematic and kind of how it works. This is the images from Osh Park. Again, a single board provides a single polarization. So to get dual polarization, imagine flipping the left image along that red dashed line. Imagine flipping it over and then putting that back to back with a second board. And so that's what the image on the right is showing. And then when you do that, you can combine them together to where both SMA ports are accessible for each polarization. The other thing is kind of hard to see. I couldn't think of a good way to visualize this, but I don't know if you guys can see my mouse, but the far left port marked B1 with the west-north indicator, when you flip that over, that matches up and lines up with B2 in the top center of the image, which becomes your, so what is on the top board, the west-east antenna, when you flip it over, it becomes the north-south antenna. So that's why the board is kind of marked that way. And yeah, so this is what it looks like when it's combined. So you can imagine a second board underneath the top board where the SMA connectors are poking through those big circles in the bottom left and bottom right, or top right, with your elements connected to the north, south, east, west indicators. The other holes are for just bonding the board together and getting a good mechanical and electrical mating, and then the 2 holes in the far left and bottom right are for the standoff for mounting inside the PVC enclosure. So that's what they look like from Osh Park. Here are what the populated boards look like. For the double Balun design for the dual polarization version, that's the right figure, and you can see both SMA connectors there with the bottom board poking up through that opening. This is a close-in view of the filters. That's the kind of key point here. So kind of to the right are the bandpass filters, and then you can see the solder jumpers in there for either selecting signal routing through the bandpass filter, or you could switch those solder jumpers over to the left and run them through the low-pass filter. And then you also can kind of see the bias T circuitry, and if you did want to power it externally and didn't want DC on the coax, you can remove the JP3 solder jumper so that you're not running DC back. There is an integrated gas discharge tube, which is a lightning arrestor feature, and then there's some protection diodes, although the protection diodes affect linearity, which I'll show in the results here in a second. So speaking of results, and again, I'll burn through these because this is the really nitty-gritty, down in the weeds benchtop RF measurements. I don't have time to show all the configurations. This is how I measured the noise figure. The key piece that you need to have to do any measurements is this mini circuits, well, it doesn't have to be mini circuits, but you need a 180-degree hybrid, which is the ZMS-CJ-21. So that device, there's a 180-degree hybrid on the Balun itself. So you need to break those signals out from your signal source and kind of feed both sides of the Balun. So that's kind of a key feature there. You can't just use like a Wilkinson power divider. There has to be the 180-degree phase shift there. And then when I was hooking up to the test equipment on the output, I had a DC block in the path. So I did a lot of calibration for all the components used for this, and all of those kind of measurements are included in the results. So I've backed out things like coax loss for the test cables and all that kind of stuff. The network analyzer I used, I had a calibration kit for all of that to get the reference points correct. Again, I don't have time to deep dive on that. I'm tooling around with the idea of writing a separate document just about the measurement process and how I did it for each one of the sets of measurements. So here we go. I'm going to kind of move quick. Credit to the Hume Center. I don't own any of this test equipment, and COVID has made it easier to take expensive things home, as long as you sign out the right paperwork with the university. The kind of small gray thing in the center is the network analyzer I use. The blue-gray device is the spectrum analyzer I use, and then the signal sources. The noise head is in there, and then the power supplies for everything. So I think the only thing I own in this picture is the Astron power supply in the bottom right and the Fluke multimeter that you can barely see on the far left. Everything else is the Hume Centers in terms of test equipment. So here's the results of the gain measurement, S21 from the network analyzer. Here's the results of, the filter response. So this is one of the things I screwed up. So I used too much. I did all the surface mount soldering by hand. Used too much solder on one of them. And I don't know if you guys remember on the listserv I mentioned when I was like, hey, I jumped ahead to some on-air measurements. One of the polarizations seemed bad. This is why. I did a deep dive on what I did wrong. And you can kind of see the zoomed in pictures of the inductors that I had to remove on the bandpass filter because I had too much solder in there and it beat it up and actually shorted out the inductor, which threw off the filter response and all of that. So that less is more when you're kind of doing things by hand and don't have a stencil for surface mount soldering. This is also how I do surface mount soldering, by the way. It's about a $15 hot plate from Amazon for doing this. So a lot of hands like to say that it's too hard to do surface mount. It is hard with how small the components are, but you don't need super expensive equipment to get it done. So here's the filter response. This is basically that same previous plot with the normalizing for peak gain. So the 3 dB bandwidth you can see is at about 4 megahertz and about 47.5. This is also the average of all 3 of the boards that I populated and tested. Elsewhere, I didn't put it in this deck. I have some of the standard error measurements on that, and basically the end result of all of that is things are fairly consistent from board to board. So here is the noise measurements. There's a lot of local EMI, RFI. I had to time these measurements with when my AC unit would kick on and kick off in the house. So it was kind of annoying, but not unexpected. I might move all this back to Hume and retake these measurements inside a nice Faraday cage that we have. But you can kind of see kind of in the upper part of the passband from maybe 25 megahertz to 50 megahertz or so. That's about what we expect for the noise performance. And that's also what I quoted in the table, right? When I said 3.87 dB noise figure, that was me taking an average of all 3 boards from 25 megahertz to 50 megahertz. Okay, so that's noise figure. The 1 dB compression point, I mentioned there are those output diodes. So actually I have 2 separate plots, one with the output diodes and one without the output diodes. So if you overdrive with the output diodes at about roughly 6 dBm output power, when you do all the math, that works out to about the clamping voltage of the output protection diodes. So that affects linearity. That's one of the things Dr. Ellingson said. They don't really provide that much protection. They're more of like an ESD protection thing. So I might get rid of those in future revisions, or just not leave them in the footprint but not populate them. So without them, you can see in the orange plot what the input. These are both input and output numbers. So about 15.5-ish dBm. This is also, I haven't had a chance yet to average all the boards. This is just the results of a single board, but again, they're all pretty consistent and similar. This is input third order intercept. It gets better when you get into the rejection region of the filters, but roughly -3-ish for the input third order intercept point. So take that, factor in the 36-ish dB of gain, and you're looking at about plus 33 dBm of output third order intercept point. This is input VSWR, output VSWR, and then now for the actual fun stuff, so on-air test measurements. Again, I'm burning through these. Hopefully we have time for questions when we get to the end. So this is the basic setup. So I oriented it with true north with the north-south antenna, so the main beam of the pattern is actually going east-west. And then the east-west elements are oriented along east-west, so their pattern is kind of north-south. That seems silly to mention, but it's easy to mix that up. The actual LWA people had problems with that when they did the install of, like, wait, am I orienting the pattern or am I orienting the elements? And they came up with a scheme where they use SMA and SMB connectors. They made the connectors different so that they wouldn't confuse themselves. So I'm going with what is the physical orientation with all of my board terminology. So that's basically how it was set up for the results I'm about to present. This is what it looked like kind of outside and in the shack. You can see the T2FD and then the cross dipole. It's a crossed inverted V dipole. It's about 5.5 foot elements in each one of the PVC pipes there. It's just 14 gauge wire for the actual element. And then the SDRs that I use to collect the measurements are on the right. Again, these are all Hume Center property. I don't own 2 X310s and 2 N210s. I wish. So this is all stuff from work that I use to take the measurements I'm about to present here. The bias tees are also from Kuhn Electronics and are also owned by the Hume Center. But I have, actually as of last night, I ordered the boards for about a $5 version of the bias tee, not the $100-ish version that you can get from Kuhn. So, okay, moving on. So here are the actual results. So the bottom line with the T2FD is it works better it's just basically a better antenna. So as expected, it overall basically performed better, but the active antenna became a pretty good contender at higher frequencies. So this is a shot at 1 megahertz, 500 kilohertz bandwidth, and basically what you can see here is that the AM filters are rejecting the band. So again, I'm taking these measurements simultaneously through this setup here. It's a dual receive chain SDR, so they're seeing the same thing. For those who can squint and see the detail there, I do have a little drop down for selecting the north-south or east-west element. So in this case, I'm selecting the north-south element of the active antenna and then comparing that to the T2FD, which is basically oriented east-west. So their patterns are kind of in the same direction. So yeah, so the filter is doing its job. At 3.8 megahertz, again, the T2FD is a better performer, kind of as expected. At 5 megahertz, T2FD again is a better performer. Now things start to get about equal, roughly. So the noise floor is a little bit higher with the T2FD, but the overall SNR, if you kind of compare signal to signal, is roughly the same. And now things actually start to get better with the active antenna. So the 10 megahertz WWV is a little bit better SNR. There is some averaging that's on here in these measurements, so you got to, again, they're just kind of like on-air spot checks, so you got to kind of take them with a grain of salt. But the carrier from WWV is pretty consistent, so you can see here there's a bit better SNR starting at about 10 megahertz. And then at 14 megahertz, again, this is kind of down in the CW or beacon area, so things are looking better. There's a little bit of averaging, though, so take it with a grain of salt. And then now switching over to, I forgot to update this figure. So this is just a bad figure. This is not 7.2 megahertz. This is a repeat. Yeah, here we go. Transitioning into the active magnetic loop. So again, kind of a wider shot. This is 4 megahertz of spectrum, where you can see that the filters in the active antenna are rejecting those AM signals, and you can only kind of see that one really strong guy. For the record, that one really strong guy is less than a mile from my house. There's a broadcast AM tower. So that's the guy that's poking through there. Down at just under 1.5 megahertz. At 4.5 megahertz, again, the active magnetic loop is a little bit better. Things are about the same, but the noise floor is pretty good. And the key thing here is my filter wasn't perfect. I didn't actually get that 1.5 megahertz-ish or 1 megahertz 3 dB cutoff. I'm closer to about 4, so I'm still kind of in the roll-off region of the lower part of the bandpass filter. And here's where things start to get better. So at 7.2 megahertz, the active antenna compared to the magnetic loop. At 10 megahertz, things are slightly better with the active antenna. And then things are pretty good at the 14 megahertz. Okay, and this is second to last slide. So to do, I'm working on, I've got about a 20-page document that I'm writing up in LaTeX that describes all of this in more detail. It's my initial design document where I'm putting everything into one document, and then I'll break it out and hopefully, if I find the time, do things like the targeted measurement document for how I took all the measurements, getting all the actual measurements themselves posted, and all the LibreOffice Calc documents that have them. One of the recommendations is the PGA 103 device over the Galley 74s from Dr. Ellingson, and he's got some good links and papers that he's written on that. I happen to use the PGA 103s a lot for VHF and UHF work, so I have some of these in the garage, so that's a fairly easy swap out to do a whole bunch more measurements with those. But the big takeaway from the PGA 103s is they're more linear, and they've got better linearity numbers, but way lower noise figure numbers. I know we're not really going for noise limited systems here, but or sky noise limited systems here, but overall it's just a better device. So it's also newer. So swapping out for those might be on the horizon, the near horizon here. Some changes to the PCB design. It was really cumbersome to actually get the wire elements mounted to the board and then all of that packaged up in PVC enclosure. So I'm thinking about making some tweaks there. And I got the bias T stuff out as of last night. I'll be doing a bunch of S parameter measurements with that to make sure it's performing how it's supposed to and not screwing up anything. And then after that, there's a ton of room for experimentation, particularly with the extraordinary and ordinary mode discrimination by having a cross dipole. So that's about it. This is my thank you slide for giving me the time to talk today. And it also shows the kind of progression of the assembly into that PVC enclosure. And so that whole kind of ring terminal to number 6 screw through the board, that's really tight and annoying, trying to get that into the PVC enclosure there. All this stuff is available at Lowe's, by the way, for the enclosure. And yeah, so that's about it. So with that, if there are any questions or go backs or comments, anything I'm obviously doing wrong, that's very happy to take criticism about why this design sucks, right? Because then I can switch gears. This is just one way to make an active antenna, right? And there's a couple of other technologies that eventually I want to take a look at. But here's where I'm at with this design.
Okay,
Zach, go ahead, Ward. I just want to say I really appreciated the presentation. I really enjoyed it, and I enjoy your the way you do your mechanical engineering enclosures just as much as the electrical part. I really like your board flipping feature there. So
yeah, that's another one I can't claim. That was genius from the LWA folks, and thankfully they had really good CAD diagram, because I was like, how does this work? How do I get dual polarization? Because I was just thinking of standoffs to stack them, but they had a really good kind of exploded view CAD drawing in one of their documents. So really, that's the LWA guys.
I thought you did a great job. I'll turn it over to Ward now.
Oh, okay, thanks. So basically, this is a very interesting, dipole project here. Obviously, the bigger antennas are going to probably outperform it to a certain extent. And I'm wondering if a larger version of the same antenna could be combined with a second, smaller version with some kind of filter and a combiner to give a wider frequency response with essentially the same characteristics between the two antennas, one say below 7 megahertz and one from 7 megahertz up. And the second point is you might want to talk to Rick Campbell, KK7B as in Bravo. Rick's an expert on balance. He teaches at Portland State, and he manages the IMS student design competition every year for Ballon design. So you might want to talk to Rick. He might have some ideas. Anyway, the suggestion about the antennas. Go ahead.
Yeah, no, definitely. One thing on that front, I just used wire elements in the kind of easily accessible PVC pipe radomes. The LWA actually uses like a spade or a blade design, which also helps with kind of wideband response, and that might help improve the low-end performance as well. But yeah, definitely, there's plenty of room for experimenting. Can you give me that call one more time, please? I got the name, but can I get the call for the
Kilo 7 Bravo.
Kilo 7 Bravo. Got it. Thank you very much. stop sharing here. Any other comments, questions, concerns? I think one thing that I maybe didn't stress enough that I was happy about is the overall cost of the system. So again, this is a dual polarization design that is less than half the cost of one active loop from DX Engineering. I know there's other designs out there and other commercial products. That just happens to be the one that I compared it against. But I'm hoping that this is kind of easy, cheap, fast for hams and other experimenters to recreate. So I was happy that the final numbers came out not so scary in terms of hobby budgets.
Yeah, I'm very excited about this, Zach. I think it'll be really interesting to see for the personal space weather station. You know, we haven't totally settled in on a design for an antenna, and it may end up being too that we have a couple different designs that we recommend people use, and based on, you know, their needs, their budgets, their priorities, their even their preferences. And I think this looks like a viable option. It looks really nice.
Excellent. Yeah, I'm hoping it's one of many solutions, and to that end, I hope I get around to making that website where I've kind of started one, but I'm learning how to use WordPress so that it's very easy. My inspiration for things like that are W1GHZ, W6PQL, right, and a host of others out there that I'm forgetting at the moment. But those guys have really great websites for DIY projects and just kind of how to get things done. And so that's kind of they're my spirit guide in my attempts to make a website of my own for projects like this. I tend to get into a lot of different side projects and then never have a really easy way of delivering that information to others. So I'm hoping that website will help do that. And GitHub is great, but it's not necessarily great for explaining why you're doing something or how you're doing something. It's, yeah, here's the code, but do you really want to write up you know, in the README document on GitHub why you did this, that, and the other? You can, but yeah, so I'm hoping that it'll be easy for folks to take advantage of this.
Hey, Zach?
Yes, sir.
Yeah, this is Carl, K9LA. I just question about that QUCS. Is that a linear simulator or is it, you know, harmonic balance or something like that, or what?
So it's a software. I'm not sure I'm going to specifically answer your question, but I'm going to try. It's a software package that's akin to like Microwave Office,
Okay.
and that it does kind of RF, and I think some of the features it doesn't have that like Microwave Office would have were the kind of true EM modeling for like taking into account like mechanical layout and things like that. But it's basically a free and open source circuit simulator and microwave simulator.
Okay.
So it does things like really quick filter design, right? When I said, okay, I'm going to aim for 1 in 50 megahertz, I just said, okay, build me a Butterworth filter that has bandpass and has these cutoff numbers, and then it auto-populated and auto-created the circuit for me with all of the ideal design values, and then I just went in and tweaked for standard value, and then reran the plots.
Okay. All right.
It can do a lot of other stuff. That's just what I use it for on this project. So hopefully that answers. It's maybe the other way of saying that is it's also kind of like Spice, like a Spice package for circuit simulation. You can do things like that in it as well.
Great. Are there any other questions?
Yeah, Zach, are you familiar with Eric Nichols' KL7AJ?
That sounds very familiar. Is he the gentleman that did the loop designs?
He had an article in QST maybe about 5 years ago or so, and the claim of his article was that all linear polarized signals on HF, once they pass through the ionosphere, they come back down as circular polarization. In fact, right-hand circular polarization. So when this project is done, you're able to see that. That would be very interesting to verify his claim.
Yeah, that's so that was in my next steps, is that phasing issue. So and for when the gentleman presented the last time we had a call, I had a question in there about MIMO cables and N210s and phase synchronization. So this also kind of bleeds over into Tangerine SDR, but making sure that you have a tight control of the phase is critical to getting those polarization measurements, which is kind of a hope and a goal of this project. But with GNU radio and UHD, there's this really finicky, annoying problem of random phase offsets between either synchronized N210s or, like I use a dual channel SDR. So they are at least consistent in that they are completely random in the respect of the phase offset between the two receive chains. So there's workarounds and things like that for that, but that's kind of one of the next steps is really getting a handle on that to make sure. Actually, I'll go ahead and say the striving goal is full Stokes parameter sort of characterization of the incident electromagnetic wave. That's what I'm hoping to kind of get to with this kind of thing.
A break,
but yeah,
Papa Echo 5 Bravo. Can I break in here? This is Papa Echo 5 Bravo.
Go ahead, Tim.
On both questions on the polarization, I am unfortunately an expert. I'm doing NVIS research. Just what John said, when you have a wave going up into the ionosphere, it splits into a left-hand and right-hand circular polarized wave. Depending on the direction with respect to the magnetic field of the Earth, both are elliptical, but you always get the right-hand and the left-hand part in the ionosphere, and you get them both back down to the ground. So you get the polarization fading, even if you transmit with a linear polarized antenna. There's only one period where you get only purely right-hand circular polarization here on the northern hemisphere. That's just before the band, just when the band opens or when the band closes. Then one of the waves gets lost into the outer space, and the other one is still reflected. On the receiver problem, I have the same with my ANN 200D. So I have full-size inverted V's for 40 meters to observe the propagation. And I have a two-channel synchronized 16-bit receiver with it, which on startup you have a random phase offset. But if you don't touch the dial and if you keep the receiver on, that phase offset remains with an ANN 200D, an Apache Labs ANN 200D. It stays within 1/10 of a degree, even with very large temperature excursions over 24 hours outside in the field. The solution to get your synchronization, if nobody solves the FPGA problem, because it's in most SDR, dual channel SDR receivers, and I hope in the Tangerine SDR they will solve this. They will be able to reset the startup phase once you retune or once you set up the receiver. But if you don't, the solution is very simple. Take a dual relay, switch it to one power splitter and a single source, and you measure the phase of that source, and you have an absolute reference. So you can still stream your signal that's coming into disk, but you also have a reference signal that will tell you what is the true zero phase difference between the two. And with that, you can do beautiful measurements. I do, and I've got several publications, scientific publications on my name on this subject, which you can all download for free from ResearchGate. Okay, yeah, so far the transmission, Papa Echo 5 Bravo.
No, that's fantastic. Yeah, I've heard of that trick for injecting the signal to get the phase calibration. But I agree. I hope future versions like the Tangerine SDR, we can control that better and not have to have. It's not I wouldn't call it a hack, but it's a bit of a workaround to have to inject that if you have full control of the design. So yeah, no, that's all fantastic.
Yeah. So the basic problem in the Hermes and derivative receivers is the FPGA implements two separate numerical controlled oscillators, one for each receiver, and you tune one and then you tune the other, and the amount of tuning time runs out different amounts of phase offset. The plan on Tangerine is when you want to use a dual receiver, that you have a single NCO in the FPGA simultaneously down converting the two different receivers.
Excellent.
That's beautiful, Tom.
And I
because it's
just
really
remembered,
important.
I quickly Googled Eric Nichols and the, what was it, KL7AJ. I should totally mention this. The ARRL radio science publication that he authored is actually what put this on my, like, the first scent of this project that I caught, right, was reading that book. And he's got a little excerpt in there that talks about, he talked a lot about extraordinary and ordinary mode waves. There's a little excerpt in there where he shows his version of the cross dipole. And that's what got me super interested in this. And then I started Googling, found LWA, and then here we are today. So yeah, I'm familiar with Eric Nichols and all that. It's a great book for radio science that he put out.
Thank you so much, Zach, and everyone. That was really good. Well,
Yeah, thank you all for giving me the time.
I think we're going to close out soon, but before we close, I just want to point out Veronica's name has changed. What's it say, Veronica?
It's my new call sign.
Atta girl.
Hey, great.
There it is. It's just
also
granted.
happy and nice.
Kilo Delta 2, Uniform Hotel, November. Congratulations.
No, also
Veronica,
happy and nice.
Very good.
Fantastic.
Congratulations.
I think from the elder statesman of amateur radio here, let me say welcome to amateur radio.
Thank you. Thank you. I'm very excited.
Well, everyone, thank you very much to our speakers, Lord N0AX and Zach KJ4QLP. I wish everyone well. Our next HamSCI Telecon will be it should be in 2 weeks. So I'll send an email out to the listserv about that as usual. If you would like to be a presenter, please just email me and I will add you to the agenda. So thank you very much. 7-3, congratulations to Veronica, and everyone have a great day.
Zach and Ward, thank you for your presentations. Very good.
Glad you enjoyed them.
you all.
73.
Take care.
Thank you. Bye-bye.
Thanks to everybody. 73.
73, thank you.
73, everybody.